Hello and welcome to part 3 of our walkthrough of exam style questions for NCEA Level 2 Mechanics. Jasmine and Ella cross a bridge on their journey. A simplified diagram of the bridge is shown below. The bridge is 40 meters long and has a mass of 42,000 kilograms. The supports are 32 meters apart, that's the number that actually matters. They are an equal distance from the center of the bridge. So first of all, we need to state the two requirements for an object to be in equilibrium. So equilibrium means two things. It means that all the torques are balanced. And it also means that all forces are balanced. So this is a definition that you should know. Equilibrium means all torques, all forces are balanced. That's a nice achieved to get us started. Okay, on to part B. The bridge is closed for repairs to strengthen its supports. Currently, the support column at end B can supply a maximum support force of 220,000 newtons. Calculate the furthest distance from support A that a 1,750 kilogram mass could be placed before support B becomes overloaded. So if we just go back up to the diagram and let's visualize what we need to do. So we've got the distance between A and B. We've been told a mass. So calculate the furthest distance from support A that a 1,750 kilogram mass could be placed. So we'll have a mass somewhere. There's our cart. So it's going to be somewhere on that bridge, which will mean, and it will be putting a weight force through the bridge, as will the mass of the bridge itself. So we'll have the weight force of the car and the weight force of the road deck itself. For the road deck, or the plank, that will always be uniform in these questions, meaning its weight force will act through its center of mass, so its center. So we know that distance then is going to be 16 meters from support A. Okay, good. And we know that the anti-clockwise torques will equal the clockwise torques. And we know that the downwards forces must equal the upwards forces as well, because this is balanced or in equilibrium. Always best with these torque questions to start off by calculating the weight forces of whatever you have got. So usually that will be the plank that your object is sitting on and the object itself. So for us, that's the bridge and the car. Doesn't matter what order we do those in. So the car's weight force, so mass times gravity. So mass of the car times gravity. So the mass of the car is 1,750 kilograms times 9.8. So the question did say an object that weighs 1,750 kilograms, but that is just like the car. So that is 17,150 newtons, because that's a force. And we'll do the same thing for the bridge. So again, it's going to be the mass of the bridge times gravity. So the mass of the bridge was 42,000 kilograms, and we times that by 9.8. And that makes 411,600 newtons. So those are our downwards forces. So to work out torque, remember, is force times distance. So we can work out the torque that the bridge will supply. We can't work out the torque that the car will apply to the support, because we don't know where it is. So this is actually quite unusual for these exam questions. Usually you're told the distance and then you're told to find the support force. This one's a little bit backwards because we know the support force, but we don't know where the object is. But what we do know is that these torques provided by the object and by the bridge will be equal to the torque provided by the support B. So we're taking the torques around A. You always, if you take the torques around one end, that means that you are finding the support force of the other end. So we know that those torques are equal because this is in equilibrium. So we do force times distance for each of these things. Let's just do this in a different color to distinguish our weight force calculations from our torque calculations. So we're going to go 411,600 times by the distance, which is 16. So we're going distance from the support. And then plus 17,150 times by, now we don't know this distance, so we'll have to put X or D, doesn't matter what you put there, just a letter. And so support B is 32 meters away from support A, and that can provide a maximum force of 220,000 newtons. So that will give the highest value of X possible, which is what we have been asked to find. So on the left-hand side, we can do 411,600 times 16. That is 6,585,600 plus 17,150x equals, and then on this side we have got 7,040,000. So now what we need to do is solve this equation for x. So we need to get x by itself. This is a linear equation. So the process we're going to follow is just moving the terms away from the x until it's by itself on the left-hand side of the equal sign. Always add or subtract before dividing. Leave division until the end. So I'm not going to divide by 17,150. I'm going to take away the 6,585,600 first. So that will leave us with 17,150x on the left-hand side. And on the right-hand side, we will have 454,400. And now divide both sides by 17,150, and that gets x by itself. And this will give us the answer, which is 26.4956, which I think we can just round to 26.50 meters. And that is the answer. That's the furthest distance from support A. So this is a merit question. Could be. For achieved, one correct torque has been calculated, and for merit, the full answer. Okay, on to part C. Jasmine and Ella stay at a new hotel. The hotel has a system to protect it in earthquakes. The system is made of extremely strong springs. Before the building was constructed, the system was tested by being loaded with a mass m. When loaded with a mass m, the springs compress by a distance x. Give an in-depth explanation of how the size of the mass of the springs needs to change in order to compress the springs at distance 1.5x from the original length. We're going to go to the formula sheet and find a formula that relates to springs. So F equals negative kx. The negative is not hugely important here. What is important, though, is the thing that's in front of the k. K is the spring constant, so that won't change. Let's just make a note of that. So k is the spring constant. So it's not asking, what happens if you change the spring. It's what happens if you change the mass. So the spring is staying the same. So K is a spring constant, that won't change. So this will not change. Always good to be as specific with your answers as you possibly can. Don't leave anything out. Okay, what this means then is if the mass is multiplied by 1.5, the force also will be multiplied by 1.5 because the force is equal to mass times gravity. So that the force on the spring is caused by the weight force. So if the mass is multiplied by 1.5, the force will also be multiplied by 1.5. Multiplied by 1.5, since F equals mg. The weight force is mass times gravity. So what that means is, so K is staying the same, so no change. So if we increase the force, X must increase proportionally. So by the same amount. So if F gets multiplied by 1.5, X gets multiplied by 1.5 as well. So this means X is also times by 1.5. And there's our answer. So for achieved, double the mass means double the force. For X, for merit, fully justified and explained what effect that has on X. Okay, on to part D. Jasmine and Ella visit a theme park on their trip. One ride at the theme park works by a system compressing springs, which then fire the roller coaster when released. A total force of 170,000 newtons would compress the springs from 6.5 meters to 4.4 meters. The total mass of the roller coaster and its occupants is 1,900 kilograms. So we haven't been told anything about the springs themselves. So what we can sort of infer from that is we're just going to treat this as one big spring effectively. Calculate the maximum speed to which this system could accelerate the roller coaster and its occupants if it was compressed to 4.4 meters. You should start by first determining the spring constant K. Well, that's nice of the question to tell us where to start. So let's do that. So F equals a negative kx. Again, the negative doesn't really matter here, so we can just go kx. So we know the force, 170,000. We don't know k. It's told us to find that. We know x, because x is the compression or extension of the spring. In this case, compression. So we've been told it can compress the springs from 6.5 to 4.4 meters. So that means x will be 6.5, take away 4.4, so that is 2.1 meters. So we're going to go k times 2.1. So to solve for k, it's being times by 2.1, so we need to divide by 2.1. So k equals 170,000 divided by 2.1, which gives an answer of 80,952.38 newtons per meter. So now that we know K, we can use one of the few other formulas that there are for springs, which is about the potential energy stored in a spring. So the reason we want to do this is because we've been asked for a speed. Now you notice that speed is not in our potential energy formula because that is half kx squared. There's no mention of speed here, but we know that energy is conserved so long as there's no sort of external forces acting on the system. So what that means is if we work out the potential energy stored in the spring and we assume conservation of energy, so all of that gets transferred to the roller coaster, then we know the kinetic energy of the roller coaster, and then we can work out the speed. So let's substitute in what we know and solve for the potential energy. So 1/2. So we know K now, because we just worked that out. And we know X is 2.1. So don't forget to square that. So that gives us 178,500 joules. So again, we know if we assume conservation of energy, that is going to be transferred into kinetic energy, so moving energy. And the formula for that is 1/2 mv squared. So we know that the kinetic energy must be 178,500 joules. So that equals 1/2 times the mass times the speed squared. So 1/2 of 1,900 is 950. Again, always nice to just do one thing at a time. So now divide by 950. You could work this out. I'm just going to leave it as a fraction. And just work it out in one go, but there'd be nothing wrong with working that out now. And then this is v squared. We want v, not v squared, so square root both sides. Wouldn't hurt to use some brackets there. So that gives a speed of 13.707. Let's round that to 13.7 meters per second would be the speed. So this is a merit question. You get achieved for calculating the spring constant or acknowledging that energy is conserved, and then merit for the full answer. But we can turn this into an excellence with part 2. What assumptions have you made in this calculation? I mentioned this before. We have assumed that energy is conserved. And what does that mean? It means that all of the elastic potential energy that was stored in the spring when it was compressed is transferred to the roller coaster. So all the elastic potential energy from the spring is transferred to the roller coaster. If you said something along the lines of no energy lost, that would also be absolutely fine. And that turns that merit into an excellence. And that is the last question. So we are done. Thank you for watching.